In this problem, we're given a spring gun oriented horizontally. It has a height of 1.5 meters above the floor, and it launches a ball bearing with an initial velocity of 6.5 meters per second. We're asked for two different things here. We want the flight time, so the time before it hits the ground, and we want the range for the projectile, which is labeled in the diagram. Range means the horizontal distance for the flight. So one thing I've already put in the diagram is where I'm choosing to put my origin. I put it on the floor, right under where the ball is released from the spring gun. So I'm going to call that y equals 0 and x equals 0. One of the key features of this projectile motion problem is with a perfectly horizontal launch, the initial y velocity is going to be 0. So I have an initial x velocity of 6.5 meters per second. And this thing is not tilted at all. So all of that initial velocity goes into the x part of it. V naught y is equal to 0 meters per second, which really simplifies the projectile motion analysis. And then I ask myself, to get the flight time, am I looking at a horizontal analysis or a vertical analysis? And I know the y value at the end of the flight. And so what I'm going to do is start with a vertical analysis of the problem. Well, the y behavior works like this. Y is equal to y naught plus v naught yt plus 1/2 at squared. That's true anytime you have a constant acceleration in the y direction. I'll just go ahead and put a y on the acceleration. And then we use the fact that for vertical free fall, the acceleration is going to be 9.8 meters per second squared pointing downward, or negative g. So to write it in general, it would look like this. And a lot of textbooks write this down separately. Minus 1/2 gt squared in that last term. And so we plug in what we know and we try to solve for the flight time. My final y position is 0 because I hit the floor. My initial y position was 1.5. My initial y velocity is 0. So that 0t term, that's gone. And then I plug in g equals 9.8. Well, negative 1/2 9.8 is negative 4.9. I'm going to add the t squared term to both sides. So I have 4.9 t squared equals 1.5. I divide by 4.9 and square root this thing. And I'm going to keep the positive value of t. So if I write plus or minus square root 1.5 over 4.9, I'm only keeping the plus because our experiment started at t equals 0. Keeping 3 sig figs, I get 0.553 seconds for the flight time. Next, I want to compute the range for the projectile, and that is clearly a horizontal thing. So I'm going to look at the horizontal behavior of the projectile. And the motion in the horizontal direction is x equals x naught plus v naught xt plus a 1/2 ax t squared. So this is true in general, provided the acceleration is constant. But specifically for projectiles, as long as you're ignoring drag forces, there's no acceleration in the horizontal direction because nothing is pushing or pulling horizontally. So for projectile motion, the x motion becomes very simple. It's constant velocity motion. Plugging in what we know and what we don't know, the final x position is r. That's what we're looking for. The initial x position was 0. The initial x velocity was 6.5 meters per second. And the flight time for the projectile to cover that range is 0.553 seconds. So this thing is just moving at 6.5 meters per second horizontally for 0.553 seconds. It's just distance equals rate times time. And to 3 sig figs, I've got 3.59 meters for the range. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.